Hello everyone. Welcome back to another class of this digital electronics. Today we will study about this programmable logic devices. So this is given in on your textbook that is called Morris Mano. So far as this programmable logic devices are concerned, these are a kind of uh, high scale integrated circuits. So in this, the circuit that is called programmable logic devices has three basic configurations. One is this called programmable read-only memory, in short, PROM. Another one is called programmable array logic, that is called PAL. And third one is called programmable logic array. So in short, we have three: this PROM, PAL, and PLA. So how they differ? So you can see in all three configurations, there are two blocks. And these two blocks are common, like AND array or array. What is this AND array? It is the array of AND gates, logical AND gates. So a lot of AND gates are there. They are arranged in particular pattern. So that is AND array. And the second one is called OR array. OR array means there are a lot of OR gates, logical OR gates, which are arranged in particular fashion. So you can see in all three, first level, this is here and here and here and. All are AND gates here. Similarly, second level is the OR level, OR gates. So these are the similarities which you can see in all three configurations, as well as the input this side and output is this side. Input is here, output is here, input is here, output is here. Now, what makes them differ from each other? So this is very important regarding this PROM, PAL, or PLA. They consist of AND array and OR array. There is an input, there is an output. So these are the common things in all three configurations of programmable logic devices. But what is the difference? The difference is here, the way which section is programmable. Programmable means here not software programmable. Programmable means here hardware wise. The way the connections between different circuits, how at what extent they are flexible or programmable. Can we program? Can we change it? Based on that, it is uh, categorized into three parts. So in PROM, if we see the first level, which is the AND array, is nothing but a kind of decoder, is a fixed, means we cannot do programming here, or we do not do programming here. However, OR array is programmable. So in PROM, OR section is programmable and AND section is fixed. Now going to PAL, you see in PAL, AND array is programmable. Is AND section will be programmable as per the given statement. Actually, what is the use of all those three configurations? Why we want programmable? Because we want to realize the circuit as per our desired, as per our expectation. Circuit should function. But these circuits are basically a common circuit which can be used by anyone through programming. So that is why the section is given. In all three, we have and OR sections. Now in PL, you can see AND array is a programmable. However, OR array is a fixed array. Just it is reverse of your PROM. So PAL is just reverse of PROM, because in PROM, AND array is programmable. Sorry, AND array is fixed. OR array is programmable. PROM and PAL, and array is programmable and OR array is fixed. So please try to understand. Just this is simple, not very. It should not be very difficult. Only it is a kind of initially memorizing. How to implement later we will see. Now third one is PLA. In PLA, it is simple. You can see both sections are programmable. So it is more flexible compared to other. So now again, going in PROM, or section is programmable. In PAL, you can see AND section is programmable, and PLA, both sections are programmable. Play, you can play with both sections. This way you can remember. So these are the now so far as block diagram of PLDs are concerned. Now let us move what is this PROM, programmable read-only memory. So just go back to your this uh, circuit here. Yeah. So in the here in this book 7.5, read only memory. So read only memory, it started from this. P comes later on when we want to make it programmable. Otherwise, initially it is ROM. So what is ROM? ROM is essentially a memory device in which permanent binary information is stored, that we know, like ROM and RAM, random access memory, and read-only memory. Read-only memory is a non-volatile memory. However, RAM is a volatile memory. In ROM, permanent memory storage is there. In RAM, we can erase after power supply is gone. So this is what is the basic definition of RAM and ROM. So we are talking about here ROM. So binary information must be specified by the designer and is then embedded in the unit to form the required interconnection pattern. So this interconnection pattern we use to program. That is why it becomes programmable. Once the pattern is established, it stays within the unit even when power is turned off and on again. So this is what is the difference between, that is why it is called non-volatile memory. Now coming on the block diagram of ROM, just to understand, because this was the first logic device as far as programmable logic devices are concerned. So you can see PROM consists of k input lines and output lines, and the size of ROM can be determined 2 to power k, that is the input line, multiplied by the number of output line. So this is the specification. So PROM consists of k inputs and output as shown in figure 7.9. The input provides the address for memory, and the output gives the data bit or the stored words that is selected by the address. The number of words in a PROM is determined from the fact that k address input lines are needed to specify 2 to power k words. Note that ROM does not have data input because it does not have write operation. It is only read. That is why there is no pin for write. So integration circuit chips have one more enable input and sometimes come with 3-state output to facilitate the construction of large arrays of ROM. So now here we have one example you can see. So and k is the input lines. Here how many input lines are there? 1, 2, 3, 4, 5. So k is equal to here 5. And how many output lines are there? We can see here 32. So n is equal to 32. So now you can see the size of this the size of this decoder is here 5 cross 32. And how many output as you can see 32 here. You can, okay. So no, output lines are there. Sorry, these are output lines. How many output lines? So there are total 8 output lines. Sorry, this is 8 output lines. 5, that is equal to 8, and the size of this decoder 2 to power n, 2 to power k into n. So here it becomes the size of ROM will be 2 to power k is 2 to power 5 multiplied by n is equal to 8. So 2 to power 5 is equal to 32 into 8. So the size of this ROM is 32 into 8. So I hope you could understand. So this is a diagram of ROM 32 cross 8. How we can, let me remind you again. So number of input line is 5, that is K. The size of ROM is equal to 2 to power K multiplied by N. N is the number of output lines. So these are the output lines here. So total number of output lines are here 8. So that is why 2 and K is equal to 5 multiplied by number of output lines 8. So 2 to power 5 is equal to 32 multiplied by 8. So this is the size of your ROM. Now, once we could understand the size, now let us see the components. What are the components? So this is a 5 cross 32 decoder, and you know in decoder that is nothing but array and array. A and D and array. So this is a array of AND logic. However, to realize any circuit, we used to put external OR gates. So here we have already 8 OR gates. So these two things are essential to realize a logic function, and that is why this ROM can be used to realize a function. Okay. So now let us see how to make. So these are the some input lines. This is the truth table. So input lines, 5-bit input lines. So from 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1. And these are the output lines. What shall be the output? So based on the given statement of the problem, we can make. However, all possible combinations are mentioned here. I think that is some word is given. Okay. So problem is given. Let us see what is this problem. Statement of the problem. Okay, there is some truth table given is 7.3 resulting configuration of this. Okay, let us see one example to realize a circuit here. 7.1 example. It says that design a combinational circuit using a ROM. The circuit accept a 3-bit number and output a binary number equal to the square of the input. So 3-bit input is there, but output is the square of the this input. So this is the truth table. Let us see. Input 3-bit A0, A1, A2. These are, and we can write number straightforward from 0, 0, 0 to 1, 1, 1. So that is 0 and that is the 7. We can write here 1, 2, 3, 4, 5, 6, and 7. And as per the statement of the problem, it says that output is the square of the input. So these are the outputs. So square of the 0 will be 0. Square of the 1 will be 1. Square of the 2 will be 4. Square of the 3 will be 9. Square of the 4 will be 16. Square of the 5 will be 25. Square of the 6 will be 36. Square of the 7 is equal to 79. So this is the input and output, relationship between input and output. And how to write down this input and output. So you can see this 0 is written here. In order to express all this 49 number, we need how many? 6 bits. So that we should know. So B0, B1, B2, B3, B4, B5. This decimal number, just to understand, that is why I wrote here also decimal number this side. Now you can see these are the numbers only, which is the square of the input number. So 0, 1, this is 4, this is 9, this is 16, this is 25, this is 36, this is 49. So I hope this truth table you could understand, because it gives the relationship between the input and output as per the statement of the problem. Now moving how to realize it. So while realizing, we can if we give little bit more thoughts, we can minimize the implementation also. So let us see what is that, what I'm talking about. So since we know there are 3 inputs, so these are the 3 inputs, that is the called K. K is equal to here 3. So size of this row will be 2 to power K. So that is the 8. That is why here name is given 8. Multiply by the number of output. So here you can see number of output is 6 as per this But this 6 can still be reduced if we apply our brain, if we apply a little bit our logic. What are those logic? Let us just try to see. So if we see that bit by bit, that is the B0. B0, this one is nothing but is equal to A0. See, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. So there's no need to use any gate. So that is why B0 is straightforward is equal to A0. So it need not to go to inside this ROM. So one bit size of add we have reduced here. Instead of uh, becoming 6, now it is 5. Now can we do further? Yes. If we see this B1 all bit is 0. So no need to again do anything. So just give B at the place of B1 0. So now only 4 outputs are remaining which need some processing, some add and or operations. For that, then use 8 cross 4 row. So ultimate size of this will be this. And this is the final truth table of your reduced truth table of row implementation of the example, that output should output accept the 3-bit input and gives the square of the input value. So this is the statement of the problem, and we could realize. Now, inside this, what are this is the block diagram. Basically, inside that word, inside that we have a decoder. We have a decoder and OR logic. We have a decoder and OR logic. So in decoder we have 3-bit, and here we will have 8-bit output. And this side we will have 4 outputs. Basically total 6 output, but not connected with the raw decoder. So here say B what is called this B1, sorry, B0 is nothing but A0, and B1 will be logic 0 here, and rest will be connected B2, B3, B3, B4, B5, etc. So make the connection as per the this logic, where we have this logic one. Now, with this, we will meet again in another class regarding how to realize circuits with PLA. So we can see here, OR sections were programmable, and section is a fixed. So PLA. Let us see the sorry. In block diagram, what we have seen regarding this OR section was programmable in the PROM. In PAL, AND section is a programmable or is a fixed. Okay, this we have to remember. So with this, thank you very much for attending this class. Soon we will meet again.